Good day, everyone. I'm Michael Johannes Aquino, Civil Engineering, second year. So, Introduction to Structural Engineering. Let us proceed to Structural Engineering Overview. First, what is a structural engineer? So, engineer, mathematics of design, architect or artist, vision, aesthetics of design, mediator, liaison between parties on a project, salesman, must sell your idea yourself. Second, what do structural engineers do? Designer, consultant, take a design and fit a structural system to that. Expert witnesses in lawsuits, inspector, fieldwork, job site inspections, oversee the materials, inspect the building, pre and post construction, demolitions, building deconstructions, structural retrofits. And the last one is what do they design? What is a structure? A system designed to resist or support loading and dissipate energy. Building structures, houses, skyscrapers, anything designed for continuous human occupation. Non-building structures, bridges, tunnels, and dams. So let us proceed to forces. Influence on an object that causes a change in a physical quantity. Considered vectors, magnitude and direction. Static force, unchanging with time, walls and floors. So dynamic force, changing with time, people, furniture. So forces, axial forces, acting along one axis directly on a point or surface. Momential force, acting along an axis at a certain distance from a point, causes a folding motion. M is equal to F times D, or force times distance. Tensile force, pulling on an object, stretching it, still shows necking when too much tensile force is applied. Compressive force, pushing on an object, collapsing it, concrete crushes when too much compressive force is applied. Strain, tensile-related property, deformation or length. Stress, compression-related property, force or area. Compare using stress strain graph. What constitutes loading? Loading is a force being enacted on the structure. Many sources of load: gravity or weight, wind, snow, earthquake, and man-made. Two types of structural loading: dead loads, static, ever present, example, walls, floors, etc. Live loads, dynamic, changing. What should we build our structures out of? Common structural materials: timber, masonry, concrete, steel, and composites. So, as you can see in the picture, how do we judge the materials? Common material properties: strength, tensile or compressive, density, hardness, ductility or brittleness, elasticity, and toughness. Strength, ability of a material to withstand loading. Tensile strength, ability of a material to withstand a pulling force. Steel is good at this, but concrete performs very poorly. So let us watch video.
Split tensile strength test on concrete. In the split tensile strength test, the tensile strength of concrete is obtained by applying a compressive force along the length of the concrete cylinder. The specimen used for this method is of cylindrical in size and dimensions of 150 mm in diameter and 300 mm in length. The instrument used for this method is the universal testing machine. The specimen is prepared in the standard manufacturing procedure and placed on the mold in layers and tamped using 25 blows for each layer. After a day, the mold is removed, and the specimen is placed in the curing tank at a temperature of 27 plus or minus 2 degrees Celsius. Depending upon the requirement, the test specimen is removed from tank and dried at 7, 14 and 28 days for testing. Draw the line on the specimens as displayed on the screen. Then, record the weight and dimension of the specimen. The specimen is placed longitudinally in the machine. A bearing strip made up of plywood is placed on both sides of the specimen and align it according to the marking. Sometimes, supplement bars are placed on top of the plywood depending upon the diameter of the specimen. Now, apply the load continuously at a rate within the range 1.2 to 2.4 MPa per minute. Finally, note down the load at which cylinder fails by developing cracks. The resultant split tensile strength is calculated by the equation 2P divided by Phi into D into L, where P is equal to load at which the specimen breaks. Thank you for watching. Stay tuned. The best is yet to come. Kindly do like, share,
So let us proceed to strength. Oh. Ability of a material to withstand loading. Wait. Compressive strength is ability of a material to withstand a pushing force. Wood, concrete, steel, and masonry perform well. So let us watch again a video.
compressive strength test on concrete. The compressive strength of a concrete is defined as the ability of the concrete to withstand specific compressive forces. Compressive strength of concrete depends on many factors such as water-cement ratio, cement strength, quality of concrete material, quality control during production of concrete, etc. Generally, the specimens shaped in cube and cylinder are used for testing the compressive strength of concrete. The standard size of a cubical specimen is 150 mm into 150 mm into 150 mm, while the cylindrical specimen is 150 mm in diameter and 300 mm in length. Generally, the fresh concrete is prepared according to the required grades and the respective mix proportion. Once the fresh concrete is prepared, the inner surface of the mold is greased to avoid sticking of concrete. The prepared fresh concrete is then filled in mold in 4 layers. After filling each layer, tamping should be done for 35 times for cube and 25 times for cylinder using a standard tamping rod. Once the mold is filled, level off the top surface with a trowel. After a day, the mold is removed and the specimens are dropped into the curing tank, at a standard temperature of 27 plus or minus 2 degrees Celsius. After 7 days, the specimen is taken out of curing tank and dried for a while. Then, the specimen is placed on the compression testing machine. The cube specimen is just placed on the bearing plate, while for cylindrical specimen, it is placed vertically. The instrument is adjusted such that the plate touches the top surface of the specimen. The load is applied gradually over the specimen at the rate of 140 kg per centimeter square per minute. The load at which the specimen fails is noted. Thus, the characteristic compressive strength is calculated from the ratio of load and the area. The test is generally done with the help of 3 specimens and tested for 7 days, 14 days and 28 days. Thank you for watching. Stay tuned.
So let us proceed now to density. Mass per unit volume of a material. Units is mass over volume, kilogram over meter cube, or pound minus meter over feet cube. Typically, materials with a high density are very strong and offer great protection. However, a high density means that they are heavy and difficult to work with. So hardness, ability of a material to resist permanent deformation under a sharp load, relates to the elasticity of a material. Diamond is a very hard substance. If we built a wall out of diamond, we could be sure that very few things would scratch it. However, diamond is incredibly expensive and not as tough as other engineering metals. It wouldn't stand up as well in impact loading versus other materials. Ductility and brittleness. Ability of a material to deform without fracture. We want materials with high ductility because they will indicate structural failure without a sudden collapse. So let us watch a video. Let us watch a video. Wait. Okay.
Welcome to Basic Sciences. Today's topic is brittle versus ductile materials, also known as ceramic versus metal. In a stress-strain graph, strain forms the x-axis and stress forms the y-axis. There is an elastic zone and a plastic zone. Brittle is a material that exhibits linear stress-strain relationship up until the point of failure. It undergoes elastic deformation only, and little to no plastic deformation. An example of a brittle material is ceramic. This is the elastic zone, and is longer in brittle materials relative to the short plastic region before breakage. A material is ductile when it undergoes large amount of plastic deformation before failure. Ceramic is brittle and metal is ductile.
So next is elasticity. Ability of a material to deform and return to its original shape. Important quantity. Young's modulus, ratio of stress to strain. Stress is equal to force over area. Strain is equal to deformation over length. Generates a stress-strain graph related to the ductility of a material. So next toughness. Ability of a material to resist fracture when stressed. Amount of energy absorbed per unit volume. Units is equal to joules over meters cube or pounds minus F over feet cube. Area under the stress strain curve, evaluated from 0 to the desired strain. So we know what properties are important in structural materials. How do the common materials stack up against each other? Timber. Advantages: cheap renewable resource, good intention, 40 MPa. Disadvantages: susceptible to fire, nature, not very hard, not very strong, and limits on shape, size. Masonry, concrete blocks, clay bricks. So, advantages of masonry: large compressive strength, cheap, good thermal properties, holds heat well. And the disadvantages is not a cohesive material. The strength could depend on the mortar, other factors. Poor tensile strength unless reinforced. Heavy material requires skilled laborers. Height restriction. And lastly, susceptible to the weather. Let us now proceed to concrete. Combination of water, cement, small aggregate, and large aggregate. These are the advantages of concrete. Very versatile, can be modified with admixtures for different effects. High compressive strength, 4 to 7 KSI, fire resistant, and lastly, many diverse sizes and shapes. Formwork. So these are the disadvantages of concrete. Long curing time, low tension strength, 0.4 KSI, fails in shear unless reinforced, fairly heavy material to work with. Let us now proceed to steel. These are the advantages of steel. High tensile and compressive strength, A36 steel, 60 KSI. Many varieties depending on your need. Carbon steel, stainless steel, and galvanized steel. Elastic material, ductile material, and many shapes and sizes. Disadvantages: expensive, limited quantities or competition, susceptible to fire rust, impurities. Reinforced concrete, concrete with steel reinforcement, concrete handles comprehension, and steel takes tension. Can handle nearly 4 times the loading that concrete alone can handle. More expensive material. So let us watch again another video.
Reinforced cement concrete. The hardened concrete is generally high in compressive strength, but its tensile strength is very low, which is generally approximately 1/10 of its compressive strength. We can say as, concrete is strong in compression and weak in tension. To strengthen the concrete section in tension, reinforcement steel is embedded into the concrete. This composite section is called reinforced cement concrete. The reinforcing steel also imparts the ductility to the concrete, which is primarily brittle. The reinforcements are embedded into the tension zone of the section to counteract the tension force acting in the section. Most of the modern-day buildings are constructed using this type of concrete. In case of compression members, reinforcing steel also acts as a supplement in bearing compressive forces. Recent times, polymers are also widely used for making reinforced concrete. We have already made a video on this, link available in the description. The usage of reinforcement such as size and numbers of reinforcement steel should be designed based on the various factors, and it also should be confined to a specific code of practice. Improper size and number of reinforcements may result in failure of the structures. Thank you for watching. Stay tuned. The best is yet to come. Kindly do like, share, comment your views and finally don't forget to subscribe our channel.
Next is composites. Engineered compounds that have different physical or chemical properties. FRP is fiber reinforced polymers. CFRP is carbon fiber reinforced polymers. Plastics, categories of glass, categories of wood. So now we know what material will best suit our needs. What should we build with it? Structural shapes, rectangle or square, triangle, interested in stability, truss, geodesic dome. Shape stability exercise. Must be split into teams of 5. Build a triangle and square. See which shape is the most stable. Can the unstable shapes be made stable? How? Rectangle. Advantages. Proficient in resisting vertical load. Disadvantages is no lateral support. Then triangle. The advantages of triangle is able to withstand lateral and vertical loading. Many triangular shapes available. The disadvantage of triangle is wide base. Rectangle. Advantage is proficient in resisting vertical load. Disadvantage is no lateral load support. Truss. Combination of square and triangle. So these are the sample pictures. Both vertical and lateral support. Geodesic dome. The advantages of the domes. Very strong shape. Gets strong as the dome size increases. Perfect load distribution. No need for structural supports. And great aerodynamic performance. Beams geared and load path. Floor, beams, girders, columns, foundation, and soil bedrock. So let us now proceed to foundations. Support the building, typically attached to columns. Types, shallow. Spread footing is concrete strip or pad below the frost line. Slab on grade, concrete pad on the surface. Deep, drilled shafts and piles. These are the sample pictures. Columns. Carry the load from floors to the foundation. Never want the columns to fail or collapse. Typically reinforced concrete or steel. Many sizes and shapes. Girders. Attach column to column. Take the load from the beams. Transfer it to the columns and generally shape as an I-beam. Beams. Attach between the girders. Take load from the flooring system. Transfer it to girders. And lastly, generally solid squares. I-beams. Flooring. Composed of a subfloor and floor covering. Usually leave space for ductwork, wiring, etc. And floor covering ranges from application to application. So these are the sample video.
Have you ever stopped? Have you ever stopped to wonder at the huge variety of buildings and structures we see all around us? Why do we just assume that houses will stay up and bridges won't fall down? The answer can be found in the work of the structural engineer. As highly trained professionals, they work with architects and surveyors to ensure that whatever they are building can sustain the loads and stresses it will have to bear. As well as improving the places where we live, they are the guardians of safe construction too. The challenges they face are diverse and require both creativity and problem-solving skills. That's why structural engineers are both designers and problem solvers too. There are specialists who account for extreme conditions such as heavy snow or coastal storms. There are seismic structural engineers who meet the challenges of construction within earthquake zones. There are those who focus on disaster relief, helping to rebuild shattered communities and restore normal life. There are engineers who specialize in renovating old buildings for continued use, whilst preserving heritage and meeting modern standards. And then there are forensic experts who investigate the reasons why some structures fail. Today, structural engineers must also face the issues of climate change, which will make structures need to endure more challenging environments over time. Sustainability is an increasingly important goal. New regulations require materials and construction techniques to create green buildings that are still strong and secure. Structural engineers are responsible for some of the most innovative concepts, projects, and designs. They are developing new technologies and techniques to create extraordinary structures that are quite literally changing the world. But the work of the structural engineer isn't just focused on groundbreaking schemes. They are also making a difference to people's lives. Buying or improving your home can be a major expense, but you could save money by consulting a qualified engineer. They identify problems early on, provide cost-effective solutions, and ensure that all regulations are properly met. They can also check that a property is structurally safe and secure, with no nasty surprises to come later on. With 27,000 members in over 100 countries, the Institution of Structural Engineers upholds and supports the highest standards of the profession as a whole. Our members have to pass some of the most stringent exams that exist. The institution's post-nominal qualifications are an internationally recognized guarantee of professional excellence and expertise. Our annual ceremony, the Structural Awards, recognizes best practice and excellence from all over the world. Our members have proved their abilities and earned their clients' trust. You can rest assured that the right professional people are working for you. So the next time you are up on the 50th floor, crossing a bridge, or simply strolling through town, stop and reflect on just how much we owe to the talents and skills of the structural engineer.
So that's all. Thank you.